already, but thank you. Julian Borrill is a senior scientist, a senior at the lab in the physics division, I think, and a senior research physicist at Space Sciences Laboratory in UC Berkeley. I say I think because I know you've had many different variations on titles over the years, but he's been here since at least 1997. If you look at his CV, he was a postdoctoral researcher, postdoc in the NERSC Center at Berkeley Lab. That's what it was called at the time.
Way back when.
What's that?
Way back when.
Way back when. So it was really great. So I think I might have been here a couple of months more than Julian, but I've pretty much known him my whole time, and so this is really I think will be a great occasion. I looked up a few stats. So he was the project PI for MP107, many of us know very well, for 21 years. That's what I saw, and just transferred that over this year.
Yep.
To Ted. That was great, and also for the Planck project for many years. And he was doing super facility and things like that before we had super facility. I know under each of those projects, he was managing like 10 different sub-projects and doing all kinds of things. So one thing I've calculated for this year is how many, I call them NERSC center hours that projects use. And so that's like a way of normalizing the center's capabilities over all the years. So MP107 and Planck have used about 73 full days of all of NERSC over that time. So that's quite a bit. And I found over 100 publications with your name on it that acknowledge NERSC. So thank you for that.
Thank you.
And you're also, at least as far back as my data goes, number 2020, you're number 4 on the NERSC list of what I call NERSC project PI years. So you add up PI projects each year, it comes up to be 69. So that's really a lot. So with that, I'm excited to hand it over to Julian. Let's see, did I stop sharing? Yes. Excellent.
Okay, so it's great to be back here. I'm not quite sure what my titles are now. I retired on the 1st of July. 1st of August, I came back as a retired retiree, so I'm kind of in this funny limbo state. But yeah, it's been quite a journey. I will talk about the science, and I will interject some of the little notes from a personal perspective of being here this long. But of course, we have to start with the fact that we're talking about cosmology. And as Lev Landau famously said, cosmologists are often error but never in doubt. And a great example of this, I think that's a good thing, mostly. There's also this there's always an XKCD. Any topic, any subject in the world, there's an XKCD, and this is a fantastic one for cosmologists. Assume pi is 1, pretty sure it's bigger than that. Okay, we can make it 10, whatever. Has historically been part of cosmology, and I want to show the way that has changed in significant part because of work done at NERSC. So what is the cosmic microwave background? We have a Big Bang. The universe is very, very hot. It's expanding. Therefore, it's cooling. At some point, it cools through 3000 Kelvin, the ionization of hydrogen. The protons and the free electrons combine and form neutral hydrogen. Suddenly, there's no electrons, free electrons for the photons to bounce off anymore, and they just free stream almost unperturbed to us today. So, can't do that, but in this image, you can see the here and now. That doesn't suggest that we are at the center of the universe. That's any observer anywhere in the universe looks out in space, and what they see are the photons coming kind of, I mean, as you go out in space, you're going back in time, you look far enough, you get to the Big Bang. We don't see that far though, because initially the photons are bouncing off the free electrons, and we see the edge of the fog. And then the photons that happen to be streaming in our direction at we call last scattering, the ones that we see, are the ones that we see today. You'll notice there is this second region in here where the universe reionizes, but it's very, very sparse reionized. So occasionally you get some interaction, either with hot gas in clusters of galaxies or gravitationally. That's fantastic because it means we've got two things going on here. We have the image of the Big Bang, this last scattering surface, and then we can use that as a backlight for everything else that happens in the entire history of the universe. And everything that happens leaves secondary anisotropy, secondary perturbations. So cosmic, because it's everywhere, microwave, stretched by the expansion to millimeter waves, about 3 Kelvin today, and background, because these are primordial. This is the universe's wallpaper rather than the furniture. And as I say, these photons have seen it all. They have interacted with the entire history of the universe, and as a consequence, they encode the tiny variations in their temperature and polarization, encode all of fundamental physics and all of cosmology. So this is an extraordinarily rich data set. For example, take the angular power spectrum, which is the correlation between all pairs of points a given angular separation apart. And we can look at that for the temperature and the 2 polarization modes. The different bumps and wiggles, the locations and the heights can answer all kinds of questions. So one of the ones we'll talk about, this bump here tells you whether space is flat or curved. The ratio, the heights of these bumps tell you how much baryonic matter, ordinary matter, there is in the universe. The bumps and wiggles here tell you how many light rayleigh particles there are. And we've got things beyond the standard model. When did the first stars form? Massive neutrino. And the big one that we're looking at these days, when did inflation happen? And measuring, there's a particular parameter that quantifies the strength, the energy scale of inflation, and the height of this bump or this bump is anticipated to be the 3rd Nobel Prize in CMB science. It was claimed a little prematurely in 2014. Definitely publish the paper before having the press conference saying we want the Nobel Prize, please, and definitely check with other experiments to see if you're right before doing that. So 2 big steps in the whole science here. 1964, Penzias and Wilson using this telescope at Bell Labs, pointing it all over the sky, trying to set it to 0 to do radio astronomy, which is an exciting new field in those days. Couldn't get it to go to 0. They couldn't get it to go to 0. They did all kinds of systematic checks. They got the same signal day and night, summer and winter. They thought it might be what they delicately described in the paper as a white dielectric substance, pigeon poop. So they got a graduate student go in there and clean out the telescope. Got rid of the pigeons. Of course, big pigeons, they flew back. Anyhow, finally, folks down in Princeton who were trying to build this experiment heard they were doing this, phoned them up and said, by the way, what you're seeing is the Big Bang. So Penzias and Wilson get the 1978 Nobel Prize for measuring the Big Bang accidentally. And then, of course, in 1992, the Kobe satellite, 2 instruments on that, one to measure the spectrum of the black body spectrum of the CMB, the other to look for these anisotropies. And George Smoot was the PI of the instrument that measured the anisotropies, so he got it's not working. There we go. He got a Nobel Prize in physics. He also got to win Are You Smarter Than a 5th Grader? He was therefore the only person to win both a Nobel Prize and $1 million for being smarter than 5th graders.
Which was the bigger prize?
So partly based on this work, the things following on from that, continuing work on this, when NERSC moved to Berkeley in 96, obviously the lab was very keen on getting all the other divisions connected with this new supercomputing center, and so George Smoot got an LDRD, and it was to do high performance computing CMB data analysis. And I had just accepted a postdoc position down on campus. The LDRD came in, as is usual, the LDRD was announced in August to start in September, and you can't defer the funding. So I moved up from campus. Money on campus was from NASA, we could get a no-cost extension. I got moved up, so I didn't come to Berkeley for the job, but that's the job I ended up with, and 27 years later, here we are. So why supercomputing? Well, we're looking for these tiny signals about a very, very, very cold mean. And so in order to get sufficient signal to noise, we have to gather an enormous data set. And interestingly, I at one point just went back through the literature and found every CMB experiment I could and tried to calculate the size of the data set by some reasonably normalized approach. a number of detectors times sampling rate times observation duration, plotted them all up, and then threw on the peak performance of the NERSC system at any time as a proxy for supercomputing power. And lo and behold, A, they're all exponential, and B, the ground and balloon-based experiments, the blue and the green, have the same exponent. It's a Moore's law exponent. So that constrains us to sit on the bleeding edge of supercomputing. Our data sets are growing as fast as computing power used to. Now you see this turnover in Moore's law, and slightly unfortunately, I should update this because both of these experiments have been significantly delayed. So that's going to tip that in some ways, fortunately. But we don't want to go too deep into that mess. So I came in 97. One of the things I was coming here to work on was the boomerang and the Maximus balloon experiments, which were circumpolar balloon flights. You sit on the edge of Antarctica in the winter, you launch the balloon and there's a circumpolar wind. 2 weeks later, you come back over, drop the balloon down and get your data. And so preparing for this, I wrote the microwave anisotropy computational analysis package, MADCAT, with a nod to Enid Blyton. We analyzed the data. We showed that the universe was flat. That was that first bump that I was showing you in the power spectra. That was a fantastic result. It spawned the MAD bench code, which was one of the first procurement codes used for NERSC procurements and benchmarking. It also happened that this was published April 2000. So it's coming to the end of my 3-year postdoc, and they have to decide whether to make me a staff member, and I get the front cover of Nature. Okay, we'll keep it there. The other thing that happened at that time was the discovery that the expansion of the universe was accelerating. No one was expecting that. The question they were asking was, what is the rate of deceleration of the universe? And it turned out the rate of deceleration was negative. And that is seen as being the thing that prompted the dark energy, the idea of dark energy. In fact, you have to do two things. You have to have two pieces of data to break the degeneracy. So the ellipse here is the supernova results. That was the completely unexpected thing that the universe was accelerating. But in order to know where you are on this, you want to bring in the CMB measurements, because the CMB measures cosmic geometry, which is set by the sum of all the components, and the supernovae measure cosmic expansion, which is set by the difference between gravity sucking and dark energy pushing. So put them together, this bit kind of gets ignored because everyone sort of assumed that the universe was flat, and we just confirmed that assumption. But really, you need both of them to come up with this concordance cosmology. Now, up till that point, everyone knew that the universe was decelerating, and so we had this set of options of what it could look like. Almost overnight, the entire field flipped. This was the often in error but never in doubt. But in fact, what was going on to me was a huge confirmation of the scientific method. We have new data. It contradicts our cherished assumptions. The assumptions have to go, not the data. And so, in fact, to me, it was a real a plus for science. What we came up with now is this new concordance cosmology. 70% of the universe is in the form of dark energy. No idea what that is. 25% is in the form of dark matter. No idea what that is. 5% is in baryons. So we have quantified our ignorance at the 95% level. This is also a very good career move, because it means you've got a lot of stuff to work at. So 2015, the Planck satellite had actually been going all along. In fact, we finished Boomerang in the early 2000s. Those who were here long enough might recall that there was a lot of transition was happening at NERSC at that time. NERSC was no longer allowed to do research-ish. So all the people who were in research positions like myself came to work one morning and found we'd been assigned to other jobs. I was going to be on the help desk. Then I was moved to the visualization group. It was a very, very strange time. And then in 2005, Bill Kramer sent me an email saying your NERSC funding has been suspended as of 3 months ago. Okay, you owe us 3 months back pay, 2006. Fortunately, just after that happened, George got the Nobel Prize. Bill was in a meeting in Washington, and the head of the Office of Science ran in and said, tell us we're supporting this work. He had to think on his feet and say, either we just fired the one person who does this, or of course we are. So Planck was the next stage. I don't know when that image has stopped, but it's supposed to. Oh, it finished. So the challenge with this is that we now have 1,000 times the data volume of the boomerang experiment, and MadCat was a fantastic scalar pack implementation, lots of dense linear algebra. We got like 90% of the theoretical peak performance on MQuery. It was fantastic stuff, but you couldn't run it for something like Planck, so we had to move to approximate methods. The approximate methods required Monte Carlos for uncertainty quantification. And so we had a whole different set of challenges to face. And so what was now a team in the Computational Cosmology Center developed, led by Ted Kisner, developed the TOAST package, which is also part of the procurement suite for NERSC 10. So time-ordered astrophysics scalable tools. When the results were published, we got front cover in the New York Times. This was the day of a DOE review of our work. So the "What have you done for me lately?" got the front cover of the New York Times above the fold. That one worked well. So TOAST has been running at NERSC for a long time. In fact, all of these codes to generate a simulation and then reduce it been running for a long time. This was 2006 on Seaborg. This was all running an instance of the Planck mission. And you can see that over the years, as every new system has come in, this first single point was when the NERSC upgrade was to double the size of Seaborg. Like all the remaining chips of that sort, double the size of Seaborg. It went up to 6,000 and some cores. And IBM's version of MPI had hardwired 4096 as the number of MPI tasks you could have. So I think they did, said 4096 to 8192 and said, can we check that this works? So we were given the whole machine to run a simulation and reduction, and that was this single data point. And it worked. And then you can see with Franklin, communication sucked. And then with Hopper, started getting very interesting trading off between NUMA effects and the cost of MPI tasks. So at low concurrencies, where the MPI tasks weren't too high, you wanted to have 4 tasks per node to just use the local memory. And when you got to very high concurrencies, you wanted to use 1 task per node because it was the MPI task overhead that was killing you. So that was a kind of interesting starting to play around with concurrency depending on the task size. But we got a 1,000-fold speed up by the time we needed to actually run this on Planck data. And as a result, we're able to generate a 10,000 realization Monte Carlo set. So that gives you 1% statistical uncertainties. Those 10,000 realizations ended up generating 1 million maps because each realization got mapped in multiple ways. And this is many orders of magnitude larger than anyone else has ever done, even though it was one of the biggest data sets available because we had the NERSC support, NERSC capabilities. I remember when BICEP claimed that they had seen this smoking gun of inflation, they talked about the fact that they had done 10 realization Monte Carlos. All their code is in IDL. So one of the comments in a talk was, either you get to complain about the number of Monte Carlos or you get to use IDL, but not both. And this was absolutely critical. The ability to do this kind of scale Monte Carlo simulation set, the uncertainty quantification, absolutely critical for precision cosmology. We're not talking about is pi 1 or 10 anymore, but we're really talking about precision. And here's an example. So cosmology is a very young science, it's only 100 and some years old. You start from basically from general relativity as a science in 1916. Certainly when I started doing cosmology, and even when I came to Berkeley, if you ask people what the Hubble constant was, the rate of expansion of the universe, there were two camps. One said it was 50, and the other said it was 100. And each of them said, one said it was 50 plus or minus 5, and the other said it was 100 plus or minus 10. Completely divergent, completely based on the biases of the researchers involved. Precision cosmology then reduced this to, oh look, the answer is actually 70 plus or minus 10. Ultra precision cosmology, starting with things like Planck, enabled by the kinds of Monte Carlo sets we're able to do, has now split us into two camps again. But now it's based on how you do the measurement. And we're really talking about precision cosmology because we're talking about 67 plus or minus 1 versus 74 plus or minus 2. So there's a significant discrepancy, probably systematic in one or both of the data sets that hasn't been teased out yet, but possibly new physics, because these are looking at such different ways of measuring this number. So it was a good joke, but it's kind of cosmology as it used to be, not cosmology as it is today. So now, going forwards, CMBS4, this will be the ultimate ground-based CMB experiment. Had to rewrite this slide because of recent events, but this project was, we kind of got to the point where you get to sort of the accelerator experiments, and you can no longer afford to have every group having their own experiment. You've just got to have one experiment and everyone work together. And that's CMBS4. So it's brought together the leading groups working at the South Pole and in the high Atacama Desert in Chile. And why do we work in those two places? This is a map of precipitable water vapor, which is the biggest obstruction to making these measurements from the ground. And blue is very, very, very low, dry. So Antarctica, Greenland, Tibet, and the Atacama Desert in Chile. And it turns out that those are all, actually Greenland and Tibet, they're very dry at certain times of the year. They're also very wet at other times of the year. Atacama and South Pole particularly are very dry, very stable year round. The big advantage of using both is that at the pole, the same sky is always overhead, rotating, but never rises and sets. So you can take a single patch of sky and drill deep on it 24/7, 365, but only about 20% of the sky is available. There's some science where you want a big sky area, so then you go to the Atacama and you can cover 70% of the sky and tease out the two different science cases. So these are both fantastic places to work. Again, we're going to be looking at another 1,000-fold increase in the data volume. So that's going to be a big challenge. But also in 2018, I guess, 19. So 2018, the collaboration formed. I became co-spokesperson and effectively deputy director because there was no directorate, co-deputy director. And then DOE, bizarrely, normally when they have a project, they pick a lead lab, they designate it by fiat. In this case, they decided to have the labs compete, which was incredibly bad for the collaboration because suddenly all the labs were fighting each other. But Berkeley Lab won in very significant part because what we could bring to the table was 20-some years of NERSC and C3, and for this project, ESNet came in as well, and we could say, okay, this is part of our proposal is we'll bring in all these resources. And so NERSC was a huge part of this project coming to Berkeley Lab, and this kind of formed a nice bookend in some ways to my full-time career, and a fantastic affirmation of the LBRD process that was started with a single postdoc culminated in $1 billion project coming to Berkeley Lab. So I think we can chalk that one up as a success. So the challenges. Our systematics are going to be 1,000 times higher on the ground than in space. We've got atmosphere, we've got ground pickup. Now we're particularly focusing on polarization. We're going to need some kind of polarization modulation to get rid of polarized atmospheric emission. So 1,000 times higher systematics. We also need to get our systematic threshold down by a factor of 100 because we're trying to pick out even fainter signals. So, we're trying to distinguish between these three dotted lines, and the solid line is the contaminating lensing of the blue signal into the green. So, we're really squeezing into this area. We've got to push the systematics floor way down. So that's all about our algorithms. And then in terms of the implementation, again, 1,000 times larger data volume. We're going from here to here on the curve, and now this one will probably push out, but it's still a substantial increase. And we're going to need to do that with something like 100 times less power watts per flop, the end of Moore's law and beginning power constrained computing. So if you put all those together in a very naive way, we'll need something like a billion-fold increase in our computational efficiency. So there's a challenge. So just to wrap it up, I'm not sure what the time's like, but so we have this unique probe, the entire history of the universe, all of fundamental physics, all of cosmology, 2 Nobel Prizes already, third one likely, just an extraordinary data set to be working with. But as we push to fainter and fainter and fainter signals, we need bigger and bigger and bigger data volumes and tighter and tighter and tighter control of systematics. It's a permanent challenge. When I first came here, wrote Madcap, I thought, okay, done that. What do I do next? And then realized that actually, every time we got a new experiment, every time we got a new supercomputer, we were either going to have to, at very least, we were going to have to look at the implementation and possibly change the algorithms too. So yeah, the algorithms and the implementations necessarily continuously evolve with the experiments and with the HPC architectures. And I would just say that the collaboration with NERSC has been spectacularly successful. $1 billion success, and we have the biggest challenges yet to come, which is why, even though I've only been doing this for 26 years or so, the 50 years allow for the 25 in the future for CMB support.
Okay, well, thank you. If I have any questions, you can type things into chat or to the Q&A.
I'll ask one first. So you have 1,000-fold more data, is what you're saying, and you put the telescopes in really great places to get data from, right?
Yes.
I mean, so what's the plan for actually getting the data from the telescopes to somewhere like NERSC to compute?
Okay, so fiber has just been connected to the Chile site for a precursor experiment, Simon's Observatory, that I'm also working with, and we were anticipating that there would be sufficient bandwidth there to stream the data from the telescope back to NERSC.
Okay.
And in fact, we've been working on one of the things that we can do with these experiments now. They are so sensitive, they have so many detectors, that we can now use them for millimeter wave transient studies. So it's not just the integrated time, but the instantaneous sensitivity is enough to see things like Planet 9. One of the problems we see every single Starlink satellite up there and satellite of that ilk. This is actually a huge challenge and may make it impossible to do this experiment. So we were actually going to stream the data back and look for the transients in fabric, in network computing, as a kind of cool thing to play with. South Pole, we were never going to get the bandwidth. So the plan there was that we would have computing on site. We would store up to 3 years data on site, ship it back on disks every year, and do the transient search in situ at the South Pole, and there's enough bandwidth to get, we've seen a transient out. And we also make maps of every hour or so's data. And so there was enough bandwidth to get the maps and the transient alerts out, and map the use of data quality and checking things working. So NSF has just announced that the South Pole is closed for business, in their all too finite wisdom. And so it looks as though we're now having to pivot to redesign this as an all Chile experiment. That will require many more telescopes because the atmosphere is significantly worse at Chile, and you can't there's one piece of science that the inflation scale that really works best staring at a single patch. And you can't do that from Chile. So it's going to take longer. We'll have multiple patches on the sky. So exactly how many telescopes running for how long and what the data volume will then end up being is still under discussion. But we're anticipating them being able to stream.
So we have a comment and a question. The comment is for Shane. He said, I regularly use the visual with all the realizations of the shifter tasks and tutorials because this was the first example of these containers at full scale for real science. Awesome. Annette asks, what aspects of NERSC do you think have been the most instrumental in serving your work successfully?
The people. I mean, the computers have been great, mostly. But I think we have had a spectacularly successful collaboration between the CMB group and NERSC, and it's been about the people. It's been about people like Shane. It's been about people who have gone the extra mile. Yourself, Richard. Worked out ways to meet our needs, and then come back to us and say, "Could you prototype this?" The Seaborg run was great for us, but it was also a good way of testing that the Seaborg worked at full scale. So it has been a very, very, I think, mutually beneficial relationship. And a fantastic collaboration. And again, I think that's part of why Berkeley became lead lab for S4.
And we want to thank you too. Someplace out there on our wall, you'll see a plaque from NASA that I'm sure was Julian's doing. Congratulating you and recognizing NERSC for their collaboration. So thank you for that. From Chris Samuel, what options are there for improving computational efficiency given your billion-fold need?
So obviously at the moment there's a big focus on getting everything running as fast as possible on GPUs. So that's going to help significantly. We are going to need to explore new algorithms, new approximations. I think there's going to be some interesting AI/ML questions about data selection. It used to be, when the Boomerang had 10-ish detectors, each one individually built. Each one you got to know by name and all its properties and knew exactly how to treat it right. Planck had 72 detectors. CMB-S4 will have between 500,000 and 1 million detectors. So it's no longer, we're no longer going to know them by name. So we have to have ways of analyzing the data and assessing data quality that do a much smarter job. And that certainly seems like an area where AI/ML would be potentially very useful and would give us ways to optimally weight the data and improve that. So that would address part of the systematics flaw. If we look at the various areas, certainly understanding polarization. This one has a big piece of just building the best experiment we can, but also doing the best simulations we can to figure out how to mitigate these systematics. Ground pickup, we build ground shields around the telescopes. Just put one in. Turns out you don't want a highly polished ground shield. It's just set by a telescope.
Whoa!
Pushing the systematics down. This is going to be algorithmic, and then on the implementation side, just really understanding how valuable particular chunks of data are. If they're not valuable enough, don't bother with them. This one is up to you guys.
So how big is the team in the sense of kind of how much person power in bringing to doing the coding and the algorithm development and all that kind of stuff?
So the CMB-S4 collaboration is about 500 people. The project, the way DOE works, there's the project piece of it and the collaboration. The project is responsible for building the experiment, running the experiment, and delivering well-characterized single frequency maps to the collaboration. And they do all the science with that. So getting the data off the telescopes, transporting it, cleaning it, understanding it, and mapping it, and providing all the simulations to support the analysis, that's all on project. And fortunately, none of the founding 4 experiments or any of the previous ground-based experiments have worked at project scale. So data analysis was always the last thing you put. The way you got funded was to max out the amount of hardware you built, and then make very optimistic assumptions about what it could do, and that gave you the best result. Can't get away with that in a project. So fortunately, because of Planck, we had some project experience and could give an idea. And so historically, ground-based experiments have had maybe half an FTE for data analysis. The plan with CMBS4 is that we eventually ramp up to 35-ish FTEs and then hold that steady through the operations. So it will be many hundreds of FTE years put into this.
Well, thank you very much. We're respectful of people's time. Should go on with questions forever. But thank you again, Julian. That was a good talk. And
My pleasure.
many more years. Thanks.